monad is a monoid in the category of endofunctors. What's the problem? It's a definition rooted in category theory, a fairly abstract field of math which studies the relationships between, well, categories. Its most fundamental building block is the object, which can represent literally anything you want. Objects can be mapped to other objects through the use of arrows, formerly known as morphisms. You could see these as ways to go from one object to another. So, in the category of cities, morphisms could represent plane routes. You'd notice that morphisms can be composed together. If you took a plane from city A to city B and then another to city C, that would be equivalent to taking a single plane from A to C. One interesting thing to note is that you can have an arrow from an object to itself. This is known as an endomorphism, with endo being Latin for from within. A collection of objects and the morphisms they have between each other is known as a category. And as the name category theory suggests, you can have as many of these as you want. You can map categories to other categories by using what is known as functors. These are kind of morphisms between categories, but they do a lot more than that. A functor from category A to category B will map every object in A to an object in B, and every morphism in A to a morphism in B. Do note that multiple objects or morphisms in A can map to the same one in B. The only rule is that structure must be preserved. This means that given a certain path which requires passing through a functor, the end result should not depend on when you went through it. Just like objects can be mapped to themselves, categories can too, by using, you guessed it, endofunctors. Unlike endomorphisms, these can have a quote-unquote observable effect, as every element in the category can be mapped to a different element of the same category. Most categories come alongside operators, which are essentially functions taking two elements of the category and returning something else. Some of these operators have properties which follow fairly common patterns. The simplest is totality, meaning that two elements of a category create another element of the same category. Most operators are total, but an exception would be integer division, as it could produce a float. You then have associativity. In other words, given a chain of multiple consecutive uses of the operator, the placement of brackets does not have an effect on the end result. Some categories have an identity element, where when combined with another object, don't have any effect. An example of this would be the number 1 for numeric multiplication. There are a few other patterns, but those are not necessary for this video. A category with a total and associative operator is known as a semigroup. If the category also has an identity element, then it becomes a monoid. We now understand every individual word of the infamous sentence, but what does it all mean put together? Well, in reality, the sentence is actually wrong. It should be that a monad in X is a monoid in the category of endofunctors of X. Take some random category, what it is doesn't matter, and let's call it X. Then, take every single functor it has from itself to itself, and put all of them in a separate category. We now have the category of endofunctors of X. But how do we make that a monoid? Well, simply we give it a total and associative operator, as well as an identity element. This category we just made is a monad. Okay, but what does this have to do with programming? Let's create a new type or class named box, which contains some value. Then we give this type a method called map, which takes a function and applies it to the contents of the box and returns a new box with the new value. This box right here is an implementation of the endofunctor pattern. Now, what if we require that the function being passed to map return an instance of the box? Considering that map starts by calling the function, the rest of the method is simply combining two boxes in order to return one. We could say that the map method is a total operation acting on the box type. In practice, this operation is associative, and this function here acts as an identity element. As such, the map method forms a monoid within the category of boxes, which I remind you are endofunctors. So even in computer science, the infamous sentence holds true. If anything didn't make sense, feel free to comment any questions you may have. Anyways, have a nice day.